Friday is so much better than Wednesday. Wow, I feel so good today. Weekend. Today our theme song is Taxman because today is tax day. Who has to do their taxes again at this point in their lives? I do as well. I actually love doing my taxes. So I did them back in February. I don't know. Yeah, I love doing taxes. I think it's actually kind of fun. I realized, I was thinking about, I woke up this morning, I was like, man, when I taught Chem 103, it was so fun being able to have things like the president of the school college and do those with me. It's so much harder with 300 plus students to sort of organize these things. I also realized there hasn't been a Sadie update in a while, so this morning before I left the house, I snapped a picture. That's pretty much what she does all the time. She just sits and looks really sad. Well, I brought her in for the workshop before exam too.
Next Wednesday.
Next Wednesday, like during the exam?
Yeah.
I don't know, maybe. I'll think about it.
I feel like no one would have any comments with this.
So let's see. Yeah, so I was just kind of having a trip down memory lane this morning. So that was when Professor Reevely came in. When President Reevely came in. I also have some video of him struggling to blow up a balloon.
Just get it straight. Hold it, you can do it.
Got it. All right. So that was good. This was me back, man, I was really looking rugged last semester. I had decided I was just never going to get a haircut or trim my beard or anything. And then this actually leads me to a little bit of a, I don't know, I thought we'd have fun for like 10 minutes this morning. We've been working harder than we're good, so I put this together really quickly. So anyway, I was reading, this is not the first time I've had like an economist anecdote. So I was reading The Economist this morning, and so they were talking about, it was in the science section, they were talking about the explosives that had been used in Brussels a few weeks back. And so I thought we could talk about at least maybe a little bit of the chemistry of the explosive, because there's actually, there are new strategies for these terrible acts, but ways to carry them out, and chemically it can still be a little bit interesting. So first off, I wanted to show you this video, and so who remembers this demo last semester? I blinded several of you, I think. So basically, this looks like it's cotton dangling from a balloon, but it is cotton, but it's not regular cotton. And so what had happened was, let's see, regular cotton is made up of cellulose, and so that's a polymer of carbohydrate. And so, you know, carbohydrates are just sugars, and they're not explosive, not very explosive at least. And so sugars tend to look like this, and they're pretty safe. But what I had done is I had soaked cotton in HNO3, which is nitric acid, right? And so what it actually had turned all that cotton, it still looks like regular cotton, but now we've basically stuck nitro groups on all of our positions. So let's see, N2NO, O, N2O, probably here at the anomeric position as well. NO2 it should be, sorry. N2, NO2. It's okay, it always comes back. I always say that. So how are you? Oh, it's okay, one moment. No. Nitrocellulose. So basically, that's not it. There we go. So basically, it put nitro groups. And so what happens is normal cotton, is it flammable?
Yeah.
Sure, it's flammable. Is it explosive? No. If you've ever like caught your T-shirt on fire, I don't know. It could happen. It probably didn't explode on you. But nitrocellulose, all those alcohols have been replaced with nitro groups. And so what happens is this, which is crazy, right? All right. So essentially, you can see the chemistry has changed quite a bit by changing those alcohols into nitro groups. And so that led me into thinking a little bit about, all right, so let's say we have this molecule. And so this is just a methyl group. So what's the name of that molecule? Yeah, you might not know. So that's toluene. So that's a relatively common solvent in organic chemistry. And so what can happen is we can actually, again, soak this stuff in some, I believe, probably nitric acid. And so what we can form is this. And I think many of you probably know. All right, so what's the name of this molecule? Trinitrotoluene, or TNT. And so what makes TNT so dangerous is if you take 2 moles of TNT and then you basically explode it, it turns into about 15 moles of gas. And so that's significant because how much space does 1 mole of gas at atmospheric pressure take up? Yeah, so 1 mole is about 22.4 liters of gas. And so 15 times 20, it's a lot of volume, right? And that's what makes this so dangerous is we're basically going to convert this relatively small amount of stuff into a huge amount of gas. I don't know, but it disrupts things, right? It displaces a lot of other stuff in the process of becoming that gas. So anyway, TNT has largely been the standard bearer in terms of what explosives are compared to. And most explosives have nitrogen in them because nitrogen produces, one of these gases that's being produced is N2 gas. And so N2 gas is really stable. And so a lot of work has been undertaken to basically detect nitrogen in these explosives, because if you can detect this nitrogen in these organic molecules, then at least you have an idea that there's potential explosive there. I've honestly always been a little worried going to an airport as a chemist because I'm afraid they're going to be like, we detect a little bit of nitrogen on you. And I'm going to be like, yeah, I've been working with it. I'm not going to lie to them, so I don't know. It's been fine thus far. I don't actually work too much in the lab anymore, so that's good. Anyway, so a lot of work has gone into detecting this nitrogen in these explosives, and so the molecule that was actually used in the Brussels attack was make sure I get this right. It was called TATP, and so what that stands for is triacetone triperoxide. So apparently, the way that this works is, so acetone, you're probably somewhat familiar with. Acetone is just this organic molecule. It's flammable, but it's not dangerous. Acetone is used all the time, and you've used it in the lab probably to clean your glassware. So it's not that bad. But what happens is apparently if you react acetone with hydrogen peroxide, and I've talked about the instability of peroxides, I think, a little bit. So oxygen-oxygen bonds aren't very stable. What you end up forming is this triacetone triperoxide, and so what that ends up looking like is something like this. And so for one thing, we've got I think this is what, 1, 2, 3, 4, 5, 6, 7, a 9-membered ring. And so there's lots of angle strain in this thing. And furthermore, there are some oxygen-oxygen bonds, which are very unstable. And so basically, this is a very unstable molecule that doesn't have nitrogen in it. So this was the molecule that was carried out, or at least used in the Brussels attack a few weeks ago. And they're turning to these sorts of chemicals because they're not as easily detectable. They don't have nitrogen in them like the vast majority of explosives had in the past. So anyway, terrible heinous acts carried out with some of this stuff, but still a little bit interesting on the chemical side. I think that's it. I think that's the end of our fun discussion, fun-ish discussion this morning. All right, so TATP, new ways to do bad things. All right. So yeah, there's no real joke there. So we'll go on and then talk some more. So last time, let's see, where did we leave off last time? We were looking at some possible electrophiles. And so yeah, basically we're going to talk about how to figure out the cases where it can go either way, either SN1 or SN2. And so we'll start off by saying, so let's imagine we have some molecule, so let's change this into a chiran ring. And so we're going to have a leaving group here. So there's going to be cases where we have our nucleophile. And so we've got two options. We've learned two mechanisms for this reaction. So if it goes SN2, we know we're going to have our nucleophile that's now on a dash. So this is still our oxygen here. The alternative is that we could go SN1. And so in SN1, what's the stereochemistry going to be? Do we have stereoselectivity in an SN1 reaction? We don't. So we're going to end up still with our inversion product, but we're also going to end up with our retention product as well. So what's the ratio there? Is there a major product of these two? No, so this is going to be a 1-to-1 ratio, and so that's what kind of makes SN1 not the best thing in the world. So in cases where it's not clear-cut, where we don't look at this and say, all right, it's obviously going to go SN2 because it's a primary alkyl halide, we're going to have to decide. Now, one thing that we're going to talk about as we go is you can think, all right.
Should that be an N?
What's up?
On the top one. You have like
Yeah, sorry. There should be a nucleophile there. All right, so we're going to have to decide. And so as a rule, we're always going to try to look for reasons to do SN2. SN2 is in general a faster reaction. And so if SN2 is going to be allowed, we want to do it. So all of this decision making comes down to, can we do SN2? If we can, let's do it and just forget about SN1. So let's say that if it's possible to do SN2, then we should absolutely do it. And so SN2 is just better. It offers stereoselectivity. There aren't carbocations that can then lead to rearrangements and things. And so SN2 is better. If you can do SN2, we should do SN2. All right, so thus far, the only way we've thought to be able to distinguish some of our reactivities, say, we can take a bromide like this. So we can see that this is a tertiary bromide. And so we can react that with some nucleophile. We'll use the iodide anion. So we've got to ask ourselves, is this going to go SN1 or SN2? What do you think? Yeah, and so in this case, we see that we've got a tertiary halide. And so is SN2 possible with a tertiary halide? It's not possible. And so when we ask ourselves, can we do SN2 because we'd really, really like to, we can't because we've got a tertiary substrate. So unfortunately, we're going to end up having to go through an SN1 mechanism. We don't have a chiral center, so we're just going to have one product, but we're going to have to go SN1. And it's going to be up to you. There's going to be a lot of decision making as we go forward in homeworks and exams on, well, is this reaction going to be SN1, SN2? And so what will, of course, the stereo chemistry implications be? So the only case we've seen thus far where we can't do SN2 are going to be cases where we have a tertiary electrophile. And so in this case, we have to say no SN2 allowed, very sadly. Okay. Some scheduler things. When are office hours today? 12:30 to 1:30. Workshop on Sunday, right? That's going to be 1 to 3. Then we have office hours Monday and Tuesday, and the exam on Wednesday. So I'll be available at least four times over the next several days. Just so everyone knows. Okay, so we've talked about electrophile, and now we're going to move on. And so for part C, what we're going to do is we're going to talk about the nucleophile. All right, so let's think back. Let's think about things in terms of SN2. So remember that for SN2, the rate of a reaction is going to be dependent on K, the rate constant, times the nucleophile, times the electrophile. And so what we find is the concentration of the nucleophile going to affect the rate?
Yeah.
Yeah, so if we double the amount of nucleophile, what's going to happen to the rate? It's going to double, right? If we basically change this from a 1 to a 2, that's going to make the entire thing be twice as fast. And so what we find here is that the concentration of the nucleophile affects the reaction rate. And so, in that case, not only does the concentration affect our reaction rate, so does our nucleophile strength. So that's what we're going to talk about for a few minutes, is the strength of nucleophiles. All right, and so essentially the nucleophile, and this is to undergo an SN2 reaction, the nucleophile must be strong enough to, we'll use the word punch. It must be strong enough to punch off the leaving group, right? Because we're going to have this concerted mechanism where everything's happening at once. So if we're going to have our nucleophile come in and our leaving group leave, well, our leaving group has to be given a reason to leave. And so it's going to have a really good reason to leave if that nucleophile is incredibly attracted to the electrophile and comes in really hot, right? And more or less it's going to kick off that leaving group. But if we don't have that really high attraction between the nucleophile and electrophile, so let's say we have a very weak nucleophile, well, it's not going to be possible for the nucleophile to come in and really punch the leaving group away. And so in that case, we wouldn't expect an SN2 reaction to happen quite as quickly. So not only does the nucleophile concentration matter, but the strength of that nucleophile matters as well. So to just kind of summarize our possibilities here, we could have a strong nucleophile, or we could have a weak nucleophile. And so in the case of a strong nucleophile, are we going to favor SN1 or SN2?
SN2.
SN2, right? The concerted mechanism. If we have a weak nucleophile, what do you think that's going to begin to favor?
SN1.
SN1, right? So the nucleophile is not going to be that attracted to the electrophile. It's going to wait around, and there's going to be an opportunity for that electrophile to go ahead and separate on its own. Yes, sir?
Does this only apply for a secondary, like, because if we have a really strong nucleophile, but it's a tertiary electrophile?
If we have a strong and we'll look at some cases like that, but if we have a strong nucleophile, but it's a tertiary electrophile, we can't do an SN2. We can never do an SN2 with a tertiary electrophile, and so it's not going to even matter at that point.
Right, so like what if you have a really weak nucleophile, but like a primary electrophile?
Yeah, and so in that,
You know what I'm saying? Does this only apply to the secondary?
yep, and we're gonna look at plenty of cases where we have different combinations of things. Yep. Really, the decisions are gonna, for the most part, come down to the secondary, where we can do either SN1 or SN2. For the most part, if you can go off of the electrophile substitution, that's almost always gonna dominate our reaction. All right, so let's think about some trends that we see in nucleophile strength. So, what affects nucleophile strength? When's our next homework due? Monday. You had to do it anyway. It's on the exam, so it's good practice. Okay, so first off, one thing that's going to affect nucleophile strength is going to be basicity. And so what we can say is that in general, and this doesn't mean always, in general, stronger bases are stronger nucleophiles. Okay, and so let's think about why that might be the case. So let's compare two things. Let's say that things that want to do this. So we'll show an acid-base reaction. So here we'll show hydroxide acting as a base. So we're just going to react it with a generic acid. And so in this acid-base reaction, what we're going to have is some electron donation to the proton. And then our acid we see is actually now starting to that kind of looks like a leaving group, right? This looks very similar to an SN2 reaction. And so we're starting to see why we can draw parallels between basicity and nucleophilicity. So in this case, we end up with, let's see, water plus A minus. So things that like to do this, which is react as an acid-base reaction, also like to do this. And so in this case, we can just, again, use hydroxide For this case, we're gonna more or less change our proton into a CH3, and we're gonna change our A into an LG. Otherwise, this is pretty much the same process. And so in this case, again, we donate electrons from our hydroxide to our methyl group. The arrow is the exact same, right? We're having the same electron movement. And so in this case, again, we've got our OH that has become connected to something else. And then we have something that's gone away, the Lg minus. And so what we're seeing is that, well, things that really like to do this reaction are probably going to want to do this reaction for the same exact reason, right? So when we think about an acid, we know there's a dipole that goes in that direction. When we think about an electrophile, we know that there's a dipole going in that direction. So there's a lot of parallels between an acid-base reaction and nucleophilic substitution reaction. So here, we're showing our hydroxide act as a nucleophile. Now, it's not a perfect parallel, and the reason that it's not a perfect parallel is when we talk about acid string, that is ultimately going to be thermodynamics, right? So that's when we use pKa's and we look at equilibria, and so that's all thermodynamic stuff. When we talk about nucleophilicity and the strength of a nucleophile, we think about how fast a reaction will take place given a certain Is that thermodynamics? Now, what is that? That's kinetics. And so ultimately, the reason why this is just a general trend is that when we talk about nucleophile strength, we're talking kinetics. When we talk about acid-base strength, we're talking thermodynamics. But there is a very strong parallel between the two. All right, so again, what we can say is that in general, a strong nucleophile is any base, and it's not all bases, but it's in general a strong nucleophile is any base with a conjugate acid of pKa greater than 11. All right, so we're talking about the conjugates of relatively weak acids. If we've got some acid that has a pKa that's higher than 11, and so something like methanol with its pKa of 15, or water with its pKa around 16 or 17, stuff up in that region, their conjugate bases are going to be really good nucleophiles. And so this is just a general trend that we can keep in mind. So if our nucleophile has a conjugate acid and its pKa is greater than 11, we're going to have a strong nucleophile. Okay, so let's look at an example. Let's say that we have, let's see. All right, so here we've got ethyl iodide. And so we're going to think about two cases. We're going to either react it with methoxide as our nucleophile, or we're going to react it with a nitrogen with a negative charge. And so in this case, we'll use a salt. We'll say that we've got this as our electrophile. So our two possibilities is that we can react with either our NH2 or we can react with our methoxide. And so in both cases, those are going to kick off. First off, we want to think to ourselves, we'd love to do SN2. And so we look at the structure of our electrophile. Are we able to do SN2 with that electrophile? Yeah, it's a primary electrophile, right? So we've got a primary electrophile. SN2 is allowed, and so we're on pace for being able to do SN2. So I'm just going to go ahead and tell you that both of these are going to be strong nucleophiles. All right, so we've definitely got a position where we're able to do an SN2 reaction. So what we want to ask ourselves is which SN2 reaction is faster? So to determine this, what we want to do is we want to think about those conjugates. Let's prove that those are, in fact, strong nucleophiles. So what's the conjugate acid of methoxide? If methoxide acts as a base and accepts a proton, what molecule does it become? That just becomes methanol, right? And so if NH2 acts as a base, what does it become? It just becomes NH3, ammonia, right? And so what we want to do is we want to think about the acidities of these molecules. So the pKa of methanol is going to be around 16. Does that qualify for methoxide being a strong nucleophile? Yeah, because its conjugate has a pKa higher than 11. And then the pKa for ammonia is somewhere around 36. Does that qualify for NH2 to be a strong nucleophile? Definitely. In fact, that's not just a little bit strong. That's an incredibly strong base, so it's also going to be an incredibly strong nucleophile. So knowing that nucleophile strength is going to affect the rate of an SN2 reaction, which is going to go faster, the top one or the bottom one? Definitely the bottom one, right? So this one is faster because NH2 is stronger than methoxide. Okay, so nucleophile strength can have a pretty big effect. Other things that can have an effect will be size. And so bigger atoms are more polarizable. So if something is going to be really polarizable, that means that we can have a temporary dipole on one end of the atom. So this is specific for atoms. All right, so when we talk about, what is an example of just an atom that we've seen act as a nucleophile? How about bromide, right? So we've seen bromide act as a nucleophile, and so I don't know if we've seen it, but we can also have iodide act as a nucleophile. And so which would you expect to be the stronger nucleophile, bromide or iodide? Definitely iodide, right? And so it's just a size thing. So we see that iodide is there in the 5th row, and so that's going to be bigger than the halogen in the 4th row. And so what we have is our stronger nucleophile of iodide. All right. However, let's see. I don't have this in my notes, but let's go ahead and just introduce ourselves to it. So we can also say that bigger molecules typically react more slowly in SN2. Let's think about why that is. So we can compare a couple of cases. Let's compare. So we've seen methoxide, and so we know that it's a strong nucleophile. Let's compare that to a base that, in a week or so will become more important to us, tert-butoxide. And so knowing what we know about the SN2 mechanism, which do you think is going to undergo the faster SN2 reaction? Why methoxide?
It's smaller.
Yeah, so when we talk about the rate of an SN2 reaction, it's determined by crowdedness, right? And so when we look at tert-butoxide, we've got a huge, massive group next to that nucleophile. So that 5-member transition state that is ultimately going to dictate how fast our reaction is going to be really high energy if we're using tert-butoxide, because tert-butoxide takes a ton of space. It's very crowded. And so what we find here is that the methoxide will be our stronger nucleophile, even though basicity-wise these things are going to be very similar. They're going to have very similar base strength, but the methoxide is going to be a much better nucleophile. In fact, this tert-butoxide, what we're going to learn, cannot do SN2. It's just too crowded. But again, this is going to become more important when we start talking about the possibilities for elimination reactions which are not on exam 3. So this is just a little bit of a preview there. All right, so finally we can talk about solvent. And so we're actually just going to say C section E, probably on Monday. All right, so we'll talk about how solvent affects our nucleophile strength on Monday. That's its own discussion. Let's see if we can put together a list of things that will react as a strong nucleophile. So let's say that a strong nucleophile, it will include the halogens. So if we have a halogen, like an F- counts here. So all of the halogens, or at least the 4 halogens that we talk about regularly, those can act as strong nucleophiles. Typically, if we have charged stuff, that's going to react as a strong nucleophile as well. And so specifically, this is going to be a negative charge. And so what that means is, say, a negatively charged oxygen. such as in hydroxide or methoxide. And let's actually just change this to an R and make it a very generic looking thing. So we've got hydroxide, any alkoxide will work. Similarly, we can say SH is a good nucleophile, and so is any RS, any sort of thiol structure. And then the same thing for nitrogen. So anytime you see a charged nitrogen, that's going to be a strong nucleophile as well. Let's see. Some other really common ones would be, say, a deprotonated terminal alkyne. And so we haven't talked about alkynes much, but do you remember what the pKa of this proton is? So it's about 25. And so it's not like other CH bonds. Other CH bonds have a pKa of 50 or so. But in a terminal triple bond, like in a terminal alkyne like this, we actually have a relatively acidic proton. It's about 25 orders of magnitude more acidic than your typical CH proton. And so we find that this is going to be a relatively common nucleophile. And it's also a way for us to form carbon-carbon bonds, which is a lot of the goal of organic synthesis. Let's see, another one is going to be azide. That's a really common one. And so azide has a structure that looks like this. And so that can act as a really good nucleophile. So that's azide with a negative charge overall. And then a cyanate ion is another way that we can form a new carbon-carbon bond. And so we have a nucleophilic carbon there. What, compared to tert-butoxide, what do these things have in common?
Small.
Yeah, so these things right here are all really skinny. And because of our transition state, which wants to have the least crowdedness as possible, this is another reason that these are really good nucleophiles. They're very, very skinny. They're going to snake their way into that crowded transition state. Let's also add something like this. So deprotonated acetic acid would also count as a charged oxygen. So we'll just toss that in there. Finally, what we'll also find is that some neutral stuff can also be a good nucleophile. And so typically, we're going to see this in two atoms. So we'll either see this in sulfur. And so our sulfur there, and uncharged sulfur is pretty much almost always a good nucleophile. That has to do with the fact that, let's see, it's got a lone pair. Why do you think sulfur might be more nucleophilic than oxygen? It's bigger. And so it's actually this odd trend where now we go down the periodic table and we see more nucleophilic atoms, but then we find that oxygen is actually a stronger base. And so that's an example of where nucleophilicity and basicity actually diverge and we don't see the same trend. So sulfur is a really good nucleophile, and then so is an uncharged nitrogen. And so nitrogen and sulfur as uncharged atoms are typically considered good nucleophiles and can do SN2 reactions. So then let's talk about weak nucleophiles. So when we talk about weak nucleophiles, our list is going to be pretty short because we try to focus in on SN2 reactions. The most important case where we can't do an SN2 is going to be any case with a neutral oxygen. Oxygen is just not strong enough as a neutral atom to be a good nucleophile. And so anytime you see, say, water, that is not a good nucleophile. Anytime you see an alcohol, that is not a good nucleophile. And that's why I had to deprotonate. I had to use the methoxide in our example, right? It's because methoxide is that's the only way we could make methanol a strong nucleophile, because methanol itself is not. And then acetic acid, which we saw in its deprotonated form above, is also not going to be a strong nucleophile. So anytime you just see neutral oxygen, is SN2 going to be possible?
No.
No. So in these cases, we say no SN2. And that's pretty much, that's going to be our list of weak nucleophiles. So that's the thing to be on the lookout when it comes to nucleophiles is basically what atoms do we have to act as a nucleophile. If the best we've got is a neutral oxygen, that's no good. Boo. All right. So let's do some examples. So let's say we have this leaving group. So over here we have sodium methoxide. So we want to ask ourselves, predict the major product here. Now, again, we can look at this. There's a bad way of thinking, which is, all right, is this electrophile going to favor SN1 or SN2, and then is this nucleophile going to favor SN2? The good way of thinking about this is, again, can we do SN2? We want to do SN2. Just look for reasons why we couldn't do SN2. When we look at the electrophiles, is there any reason we can't do SN2?
No.
It's secondary, right? We've seen that we can do SN2 with a secondary electrophile. So then what about our nucleophile? Is that a strong or a weak nucleophile? So sodium methoxide is a salt that looks like that, right? And so is that a strong or a weak nucleophile? That is a strong. Is there any reason we can't do SN2? No. Because here we've got a strong nucleophile. And so what are we going to do? What mechanism is going to proceed here? It's going to be SN2. Just look for reasons to not do SN2. If you can't find any, do it. Do SN2. And so in this case, how many products will we get? We'll get one product. So that will be the inversion product. That looks like that. That's the easy way to remember your inversion product when we're drawing line diagrams. Just flip the wedge, do a dash, or the dash, do a wedge. That is the inversion product. All right, another example. We use the same electrophile. So again, it's going to be secondary. So now we're going to react it with methanol. All right, so when we look at that electrophile, is there any reason we can't do SN2? Just the electrophile. No, because it's secondary, we know SN2 can happen. What about the nucleophile? Yeah, is it strong or weak?
Weak.
It's weak because we have a neutral oxygen now, and so we have a weak nucleophile. Can we do SN2?
No.
We can't, so what do we have to do?
SN1.
We're forced to do SN1, even though we always want to try to do SN2 if possible. How many products will we get? We'll get 2, right? We'll end up with a racemic mixture. So we still get our inversion product, but we're also going to get our retention product because we have to go through a carbocation. So in this case, we get our racemic mixture. Josh?
So on the top example, it looks like the oxygen is neutral, but then you split it into 2 parts with the sodium and the oxygen.
So does a sodium ever make a covalent bond?
No, it's not.
No. And so it's always going to be an ionic interaction. So anytime you see stuff on the left side of the periodic table, you can't have any covalent bonds. So we're going to have a salt of some kind.
Except for hydrogen, of course.
Except for hydrogen, because it's a lone wolf. It does its own thing. Yep. So that's all. That can also be a clue. If you see a sodium involved in the nucleophile, there's a good chance that there's a negative charge on that nucleophile as well. So that's going to make it a strong nucleophile. Okay, let's take a look at another one. All right, so we're going to react with again, sodium methoxide. What type of electrophile do we have? Is it?
Secondary.
It's a secondary, right? So we've got a carbon there that's connected to 2 other carbons. All right, so can we do SN2?
Yeah.
Yep. What about the nucleophile? Is it strong or weak? Strong. Can we do SN2? Is there any reason we can't do SN2? What are we going to do?
SN2.
Yeah. So we're going to do SN2. How many products? Just 1. We're going to get the inversion product. Let's say, again, we have the same electrophile. So that's going to be a secondary electrophile. And so in this case, what we're going to do is we're going to react with, let's just react it with water.
Nope.
No.
Boo. All right, so we know we can do an SN2 with our secondary electrophile. Do we have a strong nucleophile?
No.
We have a weak nucleophile. What are we forced to do? SN1. That is really unfortunate. And so what I want to do is let's just quickly define this as a solvolysis reaction. It's really, really easy. Basically, in a solvolysis reaction, the nucleophile and the solvent are the same thing. And so that is typically going to proceed as an SN1 reaction. Maybe not always, but typically. Okay, so in this case, basically we're going to take our electrophile, we're going to dissolve it. It's probably not going to dissolve that well in water, but we're going to try to dissolve it in water. And so what's going to happen is our water is the only thing that could act as a nucleophile, and so we have a solvolysis reaction. The textbook uses it a lot, and so I just wanted you to have that in your dictionary. All right, so let's think about this for a second. This reaction will, of course, proceed as an SN1, and so we're going to hit an intermediate that's a carbocation. Now, if we consider this our reaction, let's see, we have H2O. So how many products from this carbocation will we form? Should see 2. So we're going to have this plus what? Plus diastereomer, because the top chiral center is not going to change. However, do we have a possibility that we could do maybe some sort of shift and get a different product?
Yeah.
Do we have a neighboring potentially more stable carbocation?
Yeah.
We do, and so what we could also undergo will be a 1,2 hydride shift. And so in doing the 1,2 hydride shift, we'd end up with this tertiary carbocation. And so from there, how many products can we form?
2.
We could form this product plus what? Is that a chiral center?
Oh, wait.
No.
Yeah, so this is it.
Oh.
No chiral center. So this is the only product that we would form. Right, so that's because if we had the oxygen on a dash, we would say, boop, and it'd be the same exact molecule. So in this case, 3 potential products. And again, SN1, that's why we don't try to do SN1. SN1 leads down bad roads. All right, one final example. Let's take a look at this one. So we've got CH3OH. And so, in this case, can we do, what kind of electrophile do we have? Should be a primary, right? So can we do SN2? Sure, yeah. What about our nucleophile? Is it strong or weak? Yeah, it is a weak nucleophile. All right, so can we do SN2? No SN2 unless we have a good nucleophile. But then we look back over here and we see it's a primary. The only other option is SN1. Can we do an SN1 reaction with a primary electrophile? What about an allylic primary alcohol?
Yes.
Or electrophile? Yeah, so what happens is because, remember, this is one of our cases where a primary we have to actually make a decision on it. What we end up with, of course, is this in resonance with this structure. So that's going to lead to, let's see, this product along with this product plus, of course, attack from the backside. Like that. So what happens is once we form our carbocation in this allylic case, this is very similar to the radical situation. So now we have 2 carbons with carbocation-like reactivity. And so because of that, we're going to see carbocation-like reactivity at both carbons. And so the nucleophile can attack either of these carbons, and so we end up seeing ultimately 3 possible products from, again, SN1. It's complex. Stuff happens. So here we must go SN1. All right, so we'll get the next section started real quick. This is going to be part D. So we'll talk about the leaving group. Yeah, we're in good situation. We're going to be good. All right, so let's talk about the leaving group. And so the leaving group, one thing it must be is the conjugate of a strong acid. And so that's why whenever we see Ri or RBr or RCl, that's why we first started talking about leaving groups as halides, because we're going to have I minus, Br minus, Cl minus. Are those all conjugates of a strong acid? Yeah, absolutely. And so for the same reason that it is a strong acid, right, the bromine's happy to go off and do its own thing when we have HBr, it's also pretty happy to go off and do its own thing when we have an SN1 or an SN2 reaction. What about RF? Yeah, so we'd say here, nope. And that's because HF has a pKa 2 to 4, something like that. Not a strong acid, weak acid. All right, so F is not going to be a good leaving group. So basically here are our good halogen leaving groups. And so we've alluded to this, and we'll talk about this more next time, but what about something like an alcohol? And so is an OH going to be a good leaving group? Let's think about it. So if it does leave, what we're going to end up with is OH minus. And so is OH minus the conjugate of a strong acid? What is the conjugate of OH minus? Yeah, so its conjugate is H2O. And so H2O has a pKa of around 15.7. And so this is very clearly a weak acid. And so what we're finding is that OH is not a good leaving group, so no good. However, what we're going to find is that it's better than halogens. And here's the thing about halogens. Halogens are very nasty. Pollution. Gross halides in our environment. And so while halogens do make really, really, really good leaving groups, from a chemistry perspective, they're not ideal because we're going to make tons and tons of halogen waste. And so what we would like to do is actually use something like an alcohol. What we're going to learn about next time is there are actually 2 really good options for making an alcohol into a leaving group. And so we'll go through those. We'll talk about solvent effects. We'll also look at more examples, and that should have us ready for exam 3 on Wednesday. We're not what?
We're on the exam.
You mean elimination?
Yeah.
Yeah, we're going to leave elimination till after.
Good class today.
Thanks.
I learned some good things. Like if I soak my cotton shirt in nitric acid, I have a really cool party trick.
Yeah,
Probably some
dangerous.
second-degree burns.
Dangerous party trick, essentially. Yeah.
Yeah, this is kind of
I haven't been
Good,
like all
awesome. See ya. So I could, yeah. I mean, I could also recommend the salt, in which case I would kind of expect you to pick up.
And in that sense, the salt's always about that.
Could be deep, possibly. So I mean, it could be with the installation task. Basically, you know, you're going to make it right up on typically, you know, the counter on it is like Fox. You know that plus it's a lot of yeah, there's other music. So let me stop the podcast.